Alright, hi guys. I just want to do a short video on continuity to kind of help out if you miss class or something and you're wondering how does this kind of work. So, continuous functions, let's talk about them just a little bit. This is an example. Here's a graph I made up. I'm going to call it f of x of a non-continuous function. It's continuous except for at this one point. And the informal definition of continuity is if you draw a graph and you have to like lift your pencil up to draw a new piece of the graph, that means it's not continuous. This hole makes this graph not continuous. In fact, let's say this hole is at a point, we'll call it 3. And maybe it's up here at like 4. And then maybe I'll add another point to this graph. Let's say there's a hole there, and instead down here at 2 somewhere, there's a solid point. And it must be a piecewise function. Here's our f of x. Well, obviously this function's not continuous, but if I started asking about the limit as x approaches 3 for the function, it truly doesn't matter that there's a hole in that graph because the limit from the left and the limit from the right are equal to each other. And I'm going to write that down here. The limit as x approaches 3 from the left and the right, both ends, if you look at the graph, are both heading to 4. So a little bit of a run-on sentence here, but the limit from this side and from this side, the left and the right, are totally going to 4, which means overall the limit as x approaches 3 for this function is equal to 4. Which goes to show you, just because a graph has a limit that exists does not mean necessarily that the graph is continuous. So I'm going to write this down. If a limit exists, it does not guarantee continuity. It does not guarantee continuity. Doesn't mean the graph's totally continuous. It might be, it might not be. So for an example here, if I wanted this graph to be continuous, what would happen is I would need to fill in this hole. So if I really want a graph to be continuous, the limit as x approaches the value, let's change it from 3 to just being the limit for any number. So the limit as x approaches a from the left side of the function has to equal the limit as x approaches a from the right side of the function. Those have to be equal to each other. And on top of that, besides the limits matching up, the actual solid point has to exist at f of a. So all three things, it's like you're going to be checking if the limit from the left equals the limit from the right equals the point. That's how you guarantee you have a continuous function. And this is the calculus definition. This is basically the definition of a continuous function. So I'm going to write definition of continuous function. And whenever you see the word continuous in calc class, in our class, this is what you should be jumping to in your head and thinking of. Oh, the limit from the left, the right, they have to match. And so does the value, so does the point. So you're going to get all these questions, and we're going to see these throughout the rest of the course of this class, where you're asked about continuous functions, and you're going to refer back to this definition. So like one of the examples we've done in class is this example. And I'm going to put it back up here so we're kind of looking at it a little bit. We're going to say let a function f of x equal, and we're going to make up some sort of a piecewise function here. And we're going to say, how about let's let f of x equal something simple like 3 minus x if x is less than or equal to 1, and x squared plus 1 if x is greater than 1. You could draw a picture of this graph to figure out if it's continuous. You could start sketching a graph and figuring it out, or we could just prove it. So here is my question. Is f of x continuous? Is f of x continuous at the point x equals 1? At the point x equals 1. I picked x equals 1 because that's the point where the two pieces of the graph are handing off to each other, these two pieces up here. So we want to see, does it hand off in a smooth fashion so that the graph on the left and the right meet up? Is it continuous? So this is what we're going to do. If we're trying to prove continuous, then we're going to study the limit from the left, the right, and the value. We're going to look for our three things. So let's start with the limit as x approaches 1 from the left side of this function. And so you look at your piecewise and you have to decide which one of these are you going to use for the left side. Well, obviously the less than 1 is the left side of 1. This is your left and this is your right. So I'm going to do it for 3 minus x. If I want to find the limit as x approaches 1 from the right side of the function, I'm going to be picking the second equation down here, x squared plus 1. And we want to see, do these two really match up? So both limits are really easy to solve. We can, essentially plug and chug on this one, plug in the value of 1, and we're going to have 3 minus 1 equals 2 for that left side. We're going to have 1 plugged into here is 1 squared plus 1. 1 squared plus 1 is 2. So that's a really good sign. The left and the right limit are matching. So awesome, we have that. And so my last thing I want to do is I just want to figure out, well, what is f of 1? What's the actual value? Is there a solid point there? And so you're going to decide which one of these are you going to plug it into to figure out what the point is. And it's going to be the one with the equal sign up here, because it's equal to 1. And so it's this first equation, 3 minus x, so we're going to do 3 minus 1, which of course we just said is 2. And now I can safely say check, check, check. I have all three things that I need. Alright, so going on to practice a few of these, they're all a little bit different. And so I think when you're doing the homework, you just want to pay attention to, are you looking for these three things? The left limit, the right limit, and the actual value. And if you kind of have that down, you'll have continuous functions down, I think, too, at the same time. All right, hope that helps.